So I guess it's a bit out of topic. Maybe it's a platinum symposium, magmatic sulfides. So I'll talk about the potentially hydrothermal, as I believe, nickel one. But I think it's quite interesting. So thanks everyone for putting this up together. Really nice. Thanks a lot. And also I would like to start thanking everything that I will present is not only my discussion and my work, but rather a collaboration between several universities in Canada and Brazil, now here in Norway, and especially to Centaurus Metals, which is a company operating the Jaguar deposit. So without their help, this would be basically impossible. They've been very, very supportive during field and sample providing and data sharing. So thanks a lot to everyone. So the Jaguar in a nutshell, if we jump straight into it, what do we think is interesting and worth talking about? It's basically a deposit that's massive magnetite, sulfide, and apatites. The host rocks are felsic subvolcanics and granites, and it has a broader chlorite, biotite, amphibole alteration around it. And sulfides are mainly pyrite, pentlandite, and millerite, so which turns out to be a nickel deposit. So that's the intriguing, at least for us, it was quite intriguing and worth looking at it. We see that this is the dominant sulfide assemblage, so pyrite, pentlandite, millerite, pyrite, bit magnetite, and apatite, not although very apatite rich as well. And very, very locally, you have these textures like pyrrhotite, pentlandite, chalcopyrite, but always with abundant magnetite and apatite. So that's roughly why do we think it's interesting. But now let's go a little bit slow through it and seeing like some details. And I would like to make a more descriptive talk. There's a lot of discussion that either this can be an IOA deposit and kind of this apart from how IOA is formed, but the hydrothermally dominated deposit, or a typical magmatic sulfide deposit that's been altered or something like that. But I would like to, in the talk, maybe show the characteristics as I think it's an interesting example. So where is this? So we are basically in the northernmost portion of Brazil, into the Amazonian craton. We have the Carajás Mineral Province, which is have a metasedimentary volcanic sequence, a lot of transcrustal fault systems into this section. All the black bodies are layered mafic ultramafic intrusions. And within this very transcrustal faults, we have several IOCG deposits where we see indicated here in the map. And these are very structurally controlled. And in the southwestern portion of the province is where we have the Jaguar nickel deposits. This occurs in a very intersection of two regional faults, shown very well in MAG here. And we see like this two structures, and these two bodies are two layered intrusions, but within some more granitic basements, it's where we find the deposit. In between, we have a banded iron formation, an Archean banded iron formation, to concentrate a bit more into this region. The deposits can be summarized into, the map is a bit messy, but the northern portion is dominated by granitics and gneisses, whereas the southern portion is dominated by felsic subvolcanic rocks. Within the zones, we have several faults and these very subvertical zones. In the very subvertical zones is where we find these alteration halos, normally dominated, as I say, biotite and chlorite. And within this, we have this magnetite, apatite-rich rocks. So this is well constrained mainly by drill cores. There's not a lot of outcrops in the region. And although we put this as two zones here, we are talking in the talk, we have several targets that were delimited, and that's delimited by the company now. So we have a main zone southern there, so with some targets, a northern zone with few targets, and some satellite occurrences. So this is not one mineralized body, but rather a much more complex system of several of these subvertical bodies. If we look this a bit into perspective, so north up there, we have those two northern targets there, and this central major southern target with the subvertical zones and a very structurally controlled ore zone. Just a quick look on how this host rocks look. So this basically very deformed and altered granites, or which is more common into the southern portion where we have more of the mineralization, this very beautiful felsic subvolcanic rocks. And whenever I talk into magnetites or sulfides into the felsic subvolcanic rocks, I'm not referring to actually rocks, oxides that crystallized necessarily directly from these felsic rocks, but rather as these alteration pockets that start to develop where you have abundant chlorite and biotite, and then you start to find a little bit of apatite, sulfide, and magnetite, until you grade into more extensive altered zones, which have a very ductile deformation, and you have this very banded biotite chlorite dominated. Sometimes you do have a little bit of amphibole, and then you start having some disseminated or string sulfides in between. So here you have more biotite dominated and chlorite dominated domains with this tiny strings of sulfides, and then you experience also a little bit of magnetite and apatite with it. Sometimes you do see what we interpret as little relics of the felsic subvolcanic rocks being sheared and deformed into these rocks, but that's less common. Like commonly, you will only have a very dominated and obliterated rock. If we look at a bit of the general geochemical signature of the deposits as a whole, we start to see very positive correlations of sulfur and nickel with very high nickel contents into more massive ores. Arsenic here, just a proxy for how much pyrite you have. So you see like the more massive ores will be very pyrite rich as well, together with pentlandite and millerite. And copper values that are significant, but much lower than the nickel contents that we do have. Cobalt, again, up to 0.2, 0.3% into more massive ores. And again, a reflex of pentlandite and pyrite presence in these rocks. And very high phosphorus content, so up to 10%, and broadly a correlation. So the massive ores are always associated with very large amounts of apatite. Some metals, like more mobile metals, such as zinc, is just an example. You tend to form two trends. We'll see a little bit of these rocks in a while. But also, so you have nickel-rich ores with more or less zinc, but not a rule at all. If we take a look into this more expressive and dominant areas into the southern portion of it, we have, again, constrained by the real cores, we have the subvertical mineralized zones within the felsic subvolcanic rocks. The granitic domains are more in the north, we'll see them in a while. But in this case, this very structurally controlled and very deformed ores. Just one example of these drill cores, as I mentioned, you have a broader biotite chlorite alteration, that ductile rocks, and then the more mineralized and higher nickel zones is dominated by magnetite and apatite. You see that these are accompanied by phosphorus, but one thing that is interesting is that also all the apatite, I'm not going to talk much about the apatite today, but it's fluoroapatite. So it's a very fluorine-dominated system as a whole, which may play a role into nickel mobilization as one of the ideas that we have here. And we see that most of the trends that we saw before are dominated by this southern portion. So the southern portion is actually what we see as a most dominant signature in the deposit. These targets into the southern portion, they will have very deformed characteristics. So you see these very banded ores into the more distal portions where you have biotite, chlorite, and strings of sulfides more dominated by pyrite, until the more massive ores where you still have a lot of deformation and some foliation, and you have this very nice, what we call the breccias with magnetite and then a mass of sulfides and apatite. The sulfides, they are very altered, so they're not like very pristine sulfides, and we see an extensive alteration into violarite and polydimite. So mainly violarite will alters the sulfide. So you end up with a mess of very finely grained sulfides dominated by millerite, violarite within the millerite into the zones, and then nice big grains of apatite and magnetite associated with the ores. Also, it's noted like in the more deformed zones into the lower portions of the deposit, we do find this higher trends with a bit more of zinc. So you basically have, together with pyrite, chalcopyrite, and pentlandite, these are also very nickel-rich ores, as you saw in the diagrams, but some zones with basically massive sphalerite. And again, this grains here will be magnetite, and some of the other, like smaller ones, they're all apatite. We see like very nice sphalerite grains, whereas the zones that are lower into zinc, they'll be dominated by pentlandite with this violarite alterations. So very deformed and very altered ores. If we take a look at the northern portion of the deposit, like this, relatively smaller, but and straight to the north in another fault system, we see, again, very high nickel and cobalt, like the general pattern is the same, but less of that zinc-rich samples. So this tends to be more nickel and copper enriched and with fewer zinc. You see that these are now hosted within more granitic rocks, but it's still that same subvertical contact. One thing that is very interesting and started to be all this area is under exploration and development right now, so new information is coming, and some of the more recent cores started hitting some ultramafic rocks that are also associated with this northern portion of the deposit, and we'll see why that's also interesting for us in a while. Here, the deformation tends to be a little bit less. They're still deformed, but they are a little bit less foliated, more massive breccias, very abundant magnetite. Again, always associated with apatite and the sulfides. So you don't see like a decoupling of these three mineral phases at all. And the sulfides are dominantly pyrite, millerite, and pentlandite. Just a few of the examples. So we have this very nice breccias, so very brittle domain relative to that earlier chlorite, biotite, ductile zones. The dominance of pyrite, and just here, this is an outlier. It's not what is the dominant thing in the deposit, but you have some zones with pyrrhotite, pentlandite, chalcopyrite, but with much more abundant apatite and magnetite. One thing that is interesting is that you can see in some cases that sulfides that clearly cross-cut a bit the magnetites. So they are slightly later relative to the formation of the magnetites and apatites. So the sulfides come a bit later, but not extensively later, because as I say, we don't normally find zones with only sulfides. This is an example on a very thin scale. For instance, we have like this little veinlets, and in this veinlets, everything here is apatite. You have like veinlets of, and the small grains here will also be apatite. You have veinlets cross-cutting the rocks that are dominated and all the three elements associated. You have xenoliths of these earlier phases within the more mineralized and massive sulfides. And in some cases, which is again under investigation, we find this early. We have some more meta-ultramafic rocks like the stalk schists that are again associated with the ores. In these cases, you tend to have a huge amount of magnetite associated with the deposits, probably some magnetite as product of alteration of the ultramafics, and some is a part of the hydrothermal system as a whole. And finally, we do have this satellite bodies within the deposit. So all this green more zones, these are like lower contents of sulfides, but they also occur some significant mineralization. In these cases, we see that the less massive sulfides, lower nickel tenures, and lower contents of metals, no zinc association, and in some zones with much lower nickel, which we'll see a little bit in detail. Especially this target here seems to be an interesting one. It has very low nickel, which is compatible with what we see in the rock. So it's very just pentlandite solutions within pyrrhotite. And in this case, you do have some anomalous PGE values. So it's only a little bit of palladium and platinum. These are not expressive. And to best of my knowledge, they are concentrated in one of these targets in the region. But they do show like an affinity as well with some PGEs, which to us suggest a little bit as well remobilization of some magmatic sulfides at some point. Just to context this target with PGEs, it's now hosted in a diabase. It's just a diabase that crosscuts, an older diabase that crosscuts. And it's interesting, because in this case, you don't have the broader biotite chloride alteration. You just have the branches of apatite, sulfides, and magnetite. And to us, that's very nice because it shows as well that the development of this biotite chloride zones, it also depends on the host rock that you have in. It's like an interaction. So you have, when you have this more granitic felsic subvolcanics, you develop a bit of this broader alteration, but in the other places you only have this more brecciated zones, again dominated by pyrite, and magnetite and apatite is also associated. The other targets, like with slightly higher nickel tenor but lower sulfide contents, they'll basically be this stringlets of sulfides with a strong deformation. And mainly strings are disseminated sulfides, but with much lower nickel potential in more distal portions of the main mineralization. So to get some constraints about the genesis and the origin of this, and either it's a magmatic signature or more hydrothermal signature, we looked a bit into as well mineral chemistry of sulfides and oxides, which I'll quickly go through. We basically only sampled one section in the southern portion and one section in the northern portion of the deposit. There's still more work going on that we are working on, but the results that we have till now, they're only for these two sessions. We see, first of all, these are compositional maps done in laser. So one of the main features in sulfides, it's very, very nicely zoned pyrites. These are mainly zoned with cobalt, selenium, and arsenic. And one thing that shocked us and say, okay, these are exactly the same patterns that we see in magmatic sulfide deposits. Well, apart from the fact that in magmatic sulfide deposits, even in low PGE deposits, you do have a bit of IPGs into the pyrites, which are not the case for us. For us, I mean, all the PGEs are below detection limits, so very lower concentrations, and differ a bit from the magmatic sulfide. Into that more pyrrhotite, pentlandite, and chalcopyrite, very local assemblage. We do have a little bit of palladium into pentlandite, always less than 1 ppm. And the distribution of other chalcophile elements follow that in other places with this assemblage. One thing that we found interesting is that not only these are similar to magmatic sulfides, but some recent work started looking at sulfides and IOCGs. I recommend seeing Del Real. She's done very nice work with IOCG's mineral chemistry and IOCGs. Well, I took them off for some reason. And she has shown like the same oscillation patterns with the same elements and same concentric zonings in pyrite. These are also found in IOCG. So these are not an exclusive signature of magmatic sulfide deposits. We can discuss their origin if anyone is interested. In terms of mineral chemistry, we look at pyrites. We tend to differentiate magmatic and hydrothermal deposits based on pyrite chemistry. We have a very nice defined magmatic field and a hydrothermal field. But this field was mainly built based on porphyries, VMS, and low temperature hydrothermal deposits. And it turns out that when we include IOCG deposits or IOA deposits, for instance, these form their own field, which partly overlap with magmatic sulfides, but not really. And most of the analysis from the Jaguar also fall exactly within the same compositional field. So these are very similar to other IOCGs and IOA districts that we have. When we look at the oxides, one thing that is interesting is that the distribution of most elements is relatively homogeneous. We tend to have relatively high titanium and vanadium content, and just some border to core zonation, but not that typical oscillatory zoning that we see in some cases. We see, again, just looking at quickly some discriminant plots, we see that the composition of the oxides do not quite fall into that of the typical nickel copper deposits. So these are differ a bit from what we've seen in most magmatic deposits. And we see in some other plots that we see a very large range in terms of titanium and vanadium into the deposit, where some of the very small pockets into the host rocks, they seem to have higher titanium and vanadium. These are normally interpreted as more magmatic composition, but the bulk of the mineralized rocks are very typical hydrothermal concentrations relative to other, compared to other deposits as well. So this support a more hydrothermal origin as a whole. The same signature is shown. We have like quite a range of discriminant plots for magnetites, but the same trend of like slightly magmatic compositions in the host rocks to dominantly hydrothermal compositions in the bulk of the mineralization stands true for most of the most of the diagrams we decide to use. I don't necessarily think these are magmatic oxides. Basically, textural relations don't support their crystallized, like the unaltered felsic rocks don't show oxides, and these only occur into these tiny little pockets. And some recent work I'd like to recommend reading Zhang, just published a few weeks ago, that supports some high temperature magnetites in more magmatic hydrothermal systems like typical IOA systems. So that's very nice work and support, as these things can also form by hydrothermal content. So can be very tricky using only discriminant diagrams to say their origin. When we look at multi-element diagrams, these are bulk magnetites normalized to bulk crust. These were proposed by Sarah there. They give you a good overall pattern for the elements. We see one very typical characteristic of typical igneous composition oxides. And this is a mafic dike from the region that we took as an example, is that we don't have a decoupling from nickel and chromium. Nickel tends to be more mobile than chromium. And whenever you have a hydrothermal signature, you start to drop your nickel chromium more relative to nickel. When we get into the felsic subvolcanic rocks, we see that the pattern starts shifting. We start shifting also that nickel-chromium relation. And this gets progressively more evident for the more hydrothermally and mineralized zones with very much of decoupling nickel and chromium. Both into that biotite chloride alteration, that disseminated sulfides, and into this more massive magnetite and apatite mineralization zones. Indeed, the composition of the magnetites, they tend to overlap quite a lot with the nickel, especially the nickel-chromium ratio and some other elements with high temperature hydrothermal systems, but they have very, very high nickel concentrations, which have been interpreted to date like into more oxides that are associated with the alteration as well of ultramafic rocks, some ophiolite examples as well. So this higher nickel content in the oxides is normally being assigned to participation of remobilization from ultramafic rocks. And interestingly, it also overlaps quite a lot with other IOA deposits that we have in the world. So apart from, again, very higher nickel signature that we have at Jaguar relative to the other ones that we have in the world. One thing that is nice is that when we take some of the oxides, there's not much oxide chemistry data available into the other IOCGs that I mentioned in the region, but some of them, they have a similar signature, especially this one in black here. It's called Sossego, which also lies into the southern belt of mineralizations into the province. And it's interesting because it is also where we have the most of the volume of ultramafic rocks and layered intrusions into the region. Not only on the regional perspective, and we also have some other hydrothermal nickel deposits that lie into the southern belt, a little smaller, but they do also exist and are associated with the IOCGs. But in a local scale, I mean, the Jaguar deposit, the region is just next to two very big, not very big, but reasonable size layered intrusions into the region. And these are created by the same fault system. So as we can see also in the geophysical data. So our preliminary idea is that we first have more ductile alteration zones into the fault associated with forming the biotite coloration zones with purposive iron alteration, which is then cross-cutted by this magnetite apatite dominated or associated with the sulfides. The very high nickel content suggests that we are involved in the alteration of the ultramafic rocks into the region. And at least this new PGE findings that have been done as well, they support that at least some of the magmatic sulfides have been remobilized and involved into the metal sourcing for these deposits. Well, if I could summarize a little bit what I'm saying is that the Jaguar deposit, it occurs in a very regional context to other IOCGs into the Carajás province. The oxides and sulfides have chemistry that are compatible with other IOA system, iron oxide apatite systems, hydrothermally only, into the world. And discriminant diagrams only may be tricky. And to date, we are interpreting that actually the Jaguar is a nickel-rich iron oxide apatite system with, and there is a whole discussion of how IOAs themselves form, but to us, we support a predominantly hydrothermal origin to this, and with the remobilization for nickel from this ultramafic rocks into the region, and potentially some magmatic sulfides as well. There's still ongoing work. Part of the descriptive portion of the work has been published early last year. You have 2 other papers should come out soon on that. If you have any questions regarding this deposit or the Sphinx, just let us know. And again, to thank all the supporting from Centauros. They've been very cool in sharing all their data and very supportive of our work. So if you have any questions, I'll be very glad to discuss.